So here's our thought puzzle. It says, average falling speed. If a rock falls for 1 second, what's its average speed during that second? And then a follow-up question, what if the rock falls for 2 seconds? What's its average speed over those 2 seconds? Once again, we're going to vote. Well, wait a minute. Maybe we can calculate this even without a calculator. Maybe we can use some nice round numbers and then pick the answer that seems the best. So if a rock falls for 1 second, let's assume we're dropping it. If we drop it, by the way, what's VI? Zero. That one I won't tell you on a test, but I will often say the word dropped or imply that we're dropping it. What's the average speed during 1 second? One of these answers seems to me that it has to be obviously wrong. Which one?
0.
Yeah, it's moving. Its average speed can't be 0. So I would, if this was a test question, do that right away. How do we figure out speed? Well, I guess it's asking us to find VF. And that's going to be VI plus AT. Oh, we're dropping. What's VI?
0. Don't need it.
What's A?
9.8.
What if I don't have a calculator? What's a nice round number that's easy to do math with in my head, close to A? Yeah, you know what? I'm going to go 10 times 1. After 1 second, we're falling around 10 meters per second. Now, that's not what the question asked. The question said, what's the average speed? How do I find an average? Good morning, good morning. How do I find an average? If Sarah has $10 and I have $20 between us, what do we average? How do you get a 15 from a 10 and a 20? How can you go a 10 and a 20, do some math, and get 15 as an answer? Yeah. Add them up and divide by 2 if there's 2 things. Or yesterday when you found your average time, since you had 10 times, you added them all up and divided by 10. So if we add them up and divide by 2, what was VI? What was VF? Roughly, if we do the math in our head because we're lazy and don't feel like getting out a calculator? What's the average speed between 0 and 10? What's the correct answer if we use the 9.8?
4.8.
Gotta be. Right? What about after 2 seconds, what's the average speed? Again, I think we can do the same thinking. We can say, look, VI is 0. Yeah. Sorry? This answer by 2? That's a great question. Let's see if we can just double it and if that would be the correct answer. Let's find out. That might work. There's no squared. If there was a squared in the equation or a square root or something weird, I'd probably say probably not. But the fact that there's no squareds, maybe we can. Well, what would VF be after 2 seconds? It would be approximately 10 times 2, which is 20. Liam, what's the average between 0 and 20? Liam, you were right. We could have just times by 2. Nice. That, to me, that little epiphany, Liam, is worth a candy. So I told you earlier that one of my all-time favorite TV shows is the TV show Mythbusters. And one of the things that Mythbusters found was looking at water heaters. Adam Savage will tell you his favorite explosions were exploding water heaters because they were kind of, if a rocket and a bomb had a kid, you get a water heater. It's part explosion and part rocket. It's the best of all worlds. So this is one of their water heater experiments. Where am I going here, Mr. Dewick? Pause the video for a second. Mr. Dewick.
In water heater cooking, the boys were blown away by their 30-gallon water experiment. But what we didn't show you was what happened when we ramped up to a 52-gallon tank.
Small, no boom. Medium, boom. Extra large, kaboom.
It's the same type, it's set up the same way with all the safeties removed. everything's the same except it's larger. So I would expect that this is going to blow up exactly the same way, but it's going to be a little bit more energetic.
To measure just how energetic, Jamie lays out shock watch stickers around the tank.
When these water heaters explode, they make a big bang just like an explosive. Now that produces a shock wave. We want to see exactly what that shock wave is. Is it actually comparable to a couple sticks of dynamite?
At least this time, the guys know where to look. Straight up.
You want to spot how high it goes in the air?
Okay.
See if you can.
Well, that's pretty high.
Yeah.
Once again, they count up the mounting pressure.
We're at about 265 psi and climbing rapidly. So be on your guard. Anything could happen from here on in. Over. We're now at 300 psi, double what the tank's rated for. Be on your guard. Okay, everybody in here.
Lucky we were all on our guard. The heater pushed off the ground with a mighty amount of thrust.
Look at how high!
Down it comes. Now.
Wow.
Look at the guys applauding over there.
Wow, that was just around 315, and that was acting just like a rocket.
Yeah, I'm saying that went up maybe 500 feet.
The boom was commensurately louder. Whoa! And this time, knowing that it was flying up in the air, both Jamie and I took pains to watch it. And it hung for like, it had to be 12 to 13 seconds at least. It was stunning.
The telltale signs of a rocket are strewn all over the runway.
Wow, look at that.
Because that was concave.
Yeah, full bold before we started this test.
It went from like this to like that.
Jamie checks out his shock stickers.
These things register shock. They're all tripped. The green one represents 100 Gs. That's supposed to be lethal, so you'll be dead.
Note to self, never use a water heater as a drink stand.
So that's a water heater explosion. I'd like to know two things. I'd like to know how high it went, and I'd like to know its launch velocity, its VI. You okay with that? How can we figure this out? Well, first of all, I'm going to be clever. Since they want me to find part one, I'll put a part one there. Yep. Soon as it leaves the ground, it's slowing down on the way up, speeding up on the way down. We can certainly say that. Okay. Now, normally, don't write this next bit down. Normally, I would think to myself, maybe I can use this. Because in a few minutes, we're going to time how long it's in the air for. But do I know VI? Do I know how fast it left the ground for? Okay. Well, if you have a smartphone, can you get it out, please, and open up your timing device, your stopwatch?
Yes. I have it. Ready to go.
In water heater.
So the reason I picked this particular video is there is one section where they show the entire flight uninterrupted. It's right around 2 minutes, so I'll let you know when I'm going to have you start your stopwatch. I'll show you the cue. Don't start it yet. So it's right when Adam says, oh, we're going to start it. So I'm going to back up a little bit. I'll tell you when to start, and then I'll tell you when to stop. We'll see it hit the ground. That will give us the time of flight. So you ready?
I'm saying that went up maybe 500 feet.
Not that one yet. Wait for it. There.
Whoa! And this time, knowing that it was flying up in the air, both Jamie and I took pains to watch it. And it hung for like, it had to be 12 to 13 seconds.
Time. 13.6? 12.8? So I'm seeing some a bit above 13, a bit below 13. So let's do our good old take an average, about 13 seconds. We're being fairly rough. Okay, so now we have some data. T flight There's a question on the lesson 6 free fall like this. I think it's number 4, but don't quote me on that, where all I give you is the total time of flight. Here we measured it, but I could give it to you. Now, we need to realize this is the time up and back down again. And so here's where we're going to get clever. There is one velocity that I know. Which velocity do I know? I don't know VI.
0.
I know that one at the top.
Yep.
How fast are we traveling at the top for a split second? So here's what I'm going to do. I'm going to let VI be here, and I'm going to calculate how far it falls, because isn't that also how high it went? So this is the workaround we often have to do. We often won't know our VI when we're doing, in fact, the labs that we'll be doing later on today as well, you'll have to do something kind of similar. You won't know VI, but if you let VI at the top be 0, you can figure out how hard you hit the ground at. Well, that must be how hard you left the ground at, because what goes up must come down. So I'm going to make a little note here that VI is 0. I'll change back to blue. I'll change back to blue. There we go. And I think now I can find D. I'm looking for an equation that has an A, a T. Oh, wait a minute. 13 seconds all the way up and back down. I want just the time down. Okay, so now I'm going to make a little note here. T down equals 6.5 seconds. So this, I think, I can work with. Because we're starting at the top, we're going to get a negative answer because we're finding the displacement down. But that would also be the positive height up, I'm pretty sure. So you see our clever argument that we did? Which equation?
E equals VIT.
Don't waste my time.
Oh, sorry. E equals 0.5.
Or AT squared over 2. Either of those are totally acceptable. But you're right, since I got the D by itself, 0.5, negative 9.8, 6.5 squared. By the way, how many of you have ever stood on a cliff and dropped rocks down? Okay? If you've ever wondered, hey, how high is the cliff? Make sure nobody's down there, of course. But if you drop a rock and you time it on your smartphone, square the time, and then 10, half of 10, times 5. And you'll be pretty close to the height. It's actually times 4.9 if you go negative 9.8 times 0.5. But if you ever wanted to see how high it is, square the time times 5. That's how high the cliff is in meters. Kind of handy. This is pretty impressive. We get a pretty good height. That thing was up there for a while. 0.5 times negative 9.8 times 6.5 squared. I get negative 207 meters, so it was 200 meters up. Jamie Heineman, you heard him estimate about 500 feet. 1 meter is about 3 feet, so this is about 600 feet up. No, we took care of that. We divided the time by 2. We found that. Okay, so D equals, what was it, 207, negative 207 meters. Here, because it's a height, if you called it positive in your final answer, I wouldn't care. Or if you were looking at my answer key, I probably would have written positive 207, but our equation is giving us a displacement. Okay.
So that's what VI is.
What's VI?
Never mind. I read that wrong.
Okay. Well, Matt, what does part 2 want me to find?
It wants you to find how fast did the water heater leave the ground.
So
it would be VI.
It would be VI. If I wanted to, I could go like this then. VI equals question mark. VF at the top is 0. What's the time to the top? Careful, don't say 13. 6.5. Liam, what's A? Yep. Looking for an equation that has a VF, a VI, an A, and a T in it. There is one. VF equals VI plus AT. We need to get the VI by itself. How would I get the VI by itself? How would I move the AT over? Parker.
Would it be VI equals VF minus AT?
I think it would be. VF is 0, but little trick of the trade, Parker, look up. Because VF is 0, but it's also all by itself, I didn't want to cancel it right away because then you end up with only half an equation and often you'll move stuff wrong. So I left the VF in here. Now I would probably go, don't need it. But I kept it in its place because I needed that drop down like a domino reference to move the other stuff to. It's going to be negative times negative 9.8 times 6.5. What's a negative negative? Which is good because it definitely was traveling upwards when it left the ground. I should get a positive. I'm not going to bother typing the negative because they're going to cancel. It's 9.8 times 6.5. Left the ground at 63.7 meters per second. Now this is rough, but we could certainly say 60-something meters per second. Okay. And I would say that that YouTube clip is legit. They didn't do CGI or anything. Those numbers seem to make sense to me. So that's the first one I wanted to look at. Then I came across this one, next column over. This is the world record vertical jump. And we'd like to figure out how fast the jumper left the ground. I got to turn this one way down because he's got loud heavy metal music going in the background and he's going to scream. First thing is, he's going to do a legitimate vertical jump. He's not going to take a step or a run. A lot of the YouTube videos that I found, people were taking a step or a run. That's not how you measure a vertical. So he's going to jump and land on top of that. So he's pretty psyched.
That's like a small.
How tall is that, you ask? How tall is that, you ask? I'm so glad you asked. He's got a tape measure. Let's find out. Going to bring the camera. Let's zoom in. Inches, we're going to have to do a conversion. Okay. Or the US could finally go metric. 64 inches. Okay. So, first of all, what does this question want us to find?
How fast?
Yeah. D equals 64 inches. Did he end up above or below from where he started? So I don't need to put a negative in here. I do need to convert this to meters. Now, I don't know if you realize that your smart devices can do some of this, but convert 64 inches to meters.
That would be 1.63 meters.
On a test, obviously, I won't let you do that, but in your homework, or if you're just doing some nerd physics because you're looking at something and want to figure it out, use some technology and do yourself a fave. What else do I know? Because that's one thing. I need three things to find the fourth.
Acceleration, negative 9.8.
Yeah, once he left the ground, he was in free fall. Yeah.
The VF is 0.
I think at the peak of his jump, I think we can safely say that, yeah. So I'm looking for an equation that has a VI, a D, an A, and a VF in it. There is one. VF squared.
VF squared equals VI squared.
Yep. And again, you might be tempted to say, well, VF is 0, cross it out. Don't cross it out yet because it's by itself. Leave it there as your placeholder to drop down like a domino and get the VI by itself. Then you can cross out the VF. How would I get the VI by itself? Okay, so you're saying the VF squared would drop down. I would minus 2AD. Now that would leave me with a VI squared. Square root. So I'll cross out the squared. I'll square root. And now I think I would say, oh, and by the way, VF is 0. Now I'm a little nervous because there's a minus in front of the 2, and I can't take the square root of a negative. I'll get an error. Wait a minute. Is the acceleration also negative?
Oh, it
So
sure
what's a
is.
negative times a negative?
Oh, it's there.
Then I'm good with that.
There you are.
So negative 2 times negative 9.8 times 1.63. Now, we should also say that's not a true vertical jump because he bent his legs. Typically, when they measure a vertical jump, what they'll do is they'll have you reach as high as you can, measure how high that is, and then have you jump up and reach as high as you can. 'Cause they figure you're going to straighten your arms out both times, and so there's not going to be much of a difference. We are going to do a lab activity later today where you're going to measure your vertical jump, but I don't have the fancy schmancy equipment, so we're going to have to do a kind of a workaround. Do you all get 5.65? Sorry, what was that?
I think you made a calculator error. See what pretty sure. No,
Who's asking? Ronan? Yeah. What's your question? See it?
Never mind.
Okay.
I thought our D was a D.
By the way, the reason I didn't try and get the time, if we tried to time that, you'd basically be going start, stop, and I think all we'd be timing is your human reaction time, not actual good data. You know what? That'd be cool. We're going to do an activity later today where you're going to calculate your human reaction time. And the reason we have to calculate it is having your lab partner time your reaction time, all you'd be measuring is their reaction time to your reaction time. You wouldn't be getting good data. So we're going to calculate human reaction time a bit later today as well. Next page. Bart.
People, it's time we all discuss the pool safety rules. Jump, Bart, jump! Jump, Bart, jump! You got it.
Hey, Bart, your epidermis is showing.
It is?
See, epidermis means your hair. So technically, it's true. That's what makes it so funny. Pardon me a moment. Ha ha!
Hey, Nelson, he's really hurt. I think he broke his leg.
I said ha ha!
What do I want to figure out? I'd like to know how fast Bart was traveling when he hit the ground in meters per second. Then we're going to convert that to kilometers per hour. I'd like to know how high the treehouse is, and then I'd like to comment on, see if we can make a judgment on the cartoon physics. So what's number 1 asking me to find? How fast? Which velocity? VF? Give me 1 second here. Sorry, what did you say? Isn't VF 0? Oh. It's not 0 when you hit the ground. By the way, after you hit the ground, yes, but not when you hit the ground. So let's write down VF equals question mark. What we're going to do is we're going to time Bart's fall. So if you can get your smartphone stopwatch out again. And if you can get ready, and again, I'll give you a cue, and then we'll stop when we hear the thud.
Jump, Bart, jump! You got it.
Hey, Bart, your epidermis is showing.
It is?
So you ready? Start.
your hair!
Stop.
4.7.
Damn.
4.9, 4.7, 4.3. So how about a 4.5? Is it kind of sounds like a ballpark average? Do I need to divide that time by 2?
No.
Okay, that was one way. Okay, we're good. We're good. What else do we know? Now, don't get crazy with that negative 9.8. That's when you're in free fall. Every year I have some kid, we're doing a car question or something on the ground, and they're desperate. So, well, isn't a negative 9.8? No. In free fall, yes, but if I give you another application, no. We need one more thing. Oh, yeah, he fell, dropped. Looking for an equation that has a VF, a VI, an A, and a T. Oh, this is nice. I think it's our one we've used the most, and the VF is by itself already. I think I can go VF equals AT. I can even stop writing the VI. Negative 9.8 times 4.5. Negative 44.1?
Yeah.
And that's meters per second. Number 2 says, how fast in kilometers per hour? How do I convert meters per hour? By the way, we're done the unit. On your test, I'll give you 1 or maybe 2 questions in kilometers per hour. I won't give you a bunch, but the fact that cars measure speeds in kilometers per hour, I guarantee I'll give you a car question on your test, and I'll give you the VI and the VF in kilometers per hour because it's from a speedometer. But I'm not going to give you a whole bunch. Is it times by 3.6 or divide?
Fine.
Is it?
He was flying.
Austin had a really high building.
You get negative 159 kilometers per hour?
Whoa, dude.
Yep.
For the first one,
Yep.
if it was on a test,
Yep.
should it be positive?
Which way was he traveling when he hit the ground?
Down.
Negative.
But the equation is going to be like 0 minus negative 9.8 times 4.5
No, it's VF equals VI plus AT.
plus.
Look at your first equation.
Oh, yeah.
The other one where we got the VI by itself, that one was a minus. Good question. I heard Matt say, I'd like to know how high the treehouse is. So would I. D equals question mark. I don't think I'm going to relist all my data. Is there an equation that has a D, a T, an A, and a VI in it?
Oh, yeah.
Which one?
Equals VI.
No, you wasted my time.
I know. I wasted so much time.
D equals AT squared over 2, or 0.5 AT squared. Did Bart end up above or below from where he started?
Below.
This is going to give us a displacement. It's going to give us a negative answer. Negative 9.8 times 4.5. Don't forget the squared. All over 2. Negative 99 meters, so negative below 99 meters high. I'll write the negative.
I got a totally different answer.
Double check your squareds and your. I don't, by the way, you can get away without a bracket here just because even though there's more than one thing on the top, your calculators assume stuff is on the top if you hit times. So you'll notice I actually, did I do a bracket? I got away without a bracket. You could have gone though bracket, negative 9.8 times 4.5 squared, close off the top, divided by 2. You do have to have a bracket when there's more than one thing on the bottom. Or a lot of you have the newer calculators with the nice 2-level fraction button, and you're starting to see how handy that is. It also lets you see your calculator look like how you've written it, which is nice. Yeah, negative 99.2?
Yeah.
Okay. Number 4, do you think the cartoon physics is accurate? First question, 99 meters, let's round off. A football field is 100 yards, so 99 meters is about a football field. Was Bart's treehouse looking like it was the same height as a football field turned on its end? No. If Bart hit the ground at 159 kilometers per hour, is he just breaking his leg? Okay, so do you think the cartoon physics here is accurate?
No. Oh yeah. Oh yeah, for it. A long time.
Yes?
Yeah.
Okay.
Good thing it's a cartoon. Otherwise,
So if you come across a YouTube clip that's gone viral and you think it's a little sketchy, send it to me and I'll see if we can analyze it together. I mean, there was one of the classics a few years ago. Kobe Bryant did a commercial where he jumped over a pit of snakes. No, it was CGI. You can run the numbers. He did not jump that, right? Yeah.
There's a video of LeBron throwing a full court shot and not even trying.
Send me the link. D. A few years ago, Felix Baumgartner skydived from outer space.
whoa.
It looked like this.
That seems impossible. Goes to the atmosphere.
We got to get Felix off the ground safely and not tear the balloon. And we need optimum conditions. So, as the weather person here, we're going to be very, very, very picky and picking the right conditions.
Felix has completed his physical.
I've been working 4 years on the program. I believe in what Felix is trying to do to test the next generation for.
Joe Kittinger is an interesting person, also one of my nerd heroes. He worked for the U.S. Air Force, and in the 1950s, he went up in a weather balloon to the edge of space, and he's the current record holder. He jumped from about 99,000 feet. He was testing NASA's spacesuits. How do you test a spacesuit? Well, you've got to get somebody up to a near vacuum, and he was testing, could astronauts actually eject or jump out from that altitude? So they brought him on board because he's the only other person who knows what Felix might be going through. So he was Felix's mentor during this.
And I'm just delighted to be a member of the team.
This is mission control at this time. Felix is departing his Airstream trailer to be strapped into a Stratos capsule.
I will assess the situation again. We will not start inflating as soon as the balloon's completely laying out. So there'll be another small hold.
T-minus 1 hour, 13 minutes. We're going to go on hold.
Chuck Yeager was the first man to go supersonic in an aircraft. It was 65 years ago, and I think it would be just absolutely wonderful if we could get Felix to go supersonic without an airplane on the same day that Chuck Yeager flew supersonic in an airplane.
At this time, we have begun balloon inflation. Capsule systems are green, instrumentation's green, payload's green, medical systems are green.
So they had tried this about a week earlier, but it was too windy. In fact, I think one of their balloons burst when they were trying to inflate it. So they had to reset, come back another day.
There's the release, and there's the applause, a successful rise.
This is mission control. Felix's current altitude is 25,300 feet.
We're at 108,000 feet. There is an issue with the heat in the faceplate. Mission for the time being is continuing.
So something was going wrong with the faceplate heater. It was fogging up, which means he can't see. You sort of need to be able to see to do this. And so they were possibly going to have to scrub the mission, but they decided that he could see, if he kind of tilted, he could see above the fog near where his mouth was.
As the team considers what are the options, So the decision has been made. Baumgartner will jump.
So he's high enough he can clearly see the curvature of the Earth. The sky at this altitude is no longer blue during the day. It is black.
He's that high that he can see fire in the world.
Oh yeah.
I thought the satellites can't even see that.
Oh yeah, they can. They're far higher. This is not even low Earth orbit. This is low still. But we would consider this outer space because it's a near vacuum. There's still enough air for the balloon to float, but it's a near vacuum. And often we consider you to be in outer space if the sky is black during the day. Felix suffers from claustrophobia, very severe claustrophobia, so he also had to really psych himself up to stay in this enclosed area for this time.
Really high. Oh, yeah. I'm going nowhere.
So right now he's feeling almost no air resistance because the air is so thin. And he runs into an issue in a few minutes. He starts to go into a very fast spin. Normally, if you're skydiving, you counteract it by just pushing against the air because you're falling fast enough that there's air resistance. Here, he can't do that, and so that he was in danger of blacking out. You watch.
Speed 650 miles per hour. Speed 725.
There's the spin.
Speed 720.
But as he's falling, he's getting into thicker and thicker air, and so he was able to reach a place where he was able to stabilize.
Felix at a stable descent.
When you're standing out there on that step, on top of the world, and you become so humble. At that moment, it's not about breaking records anymore.
So, I went to the website and I got the data. So his initial height was 38,970 meters. After free falling for 50 seconds, he reached his maximum vertical speed. Why didn't he keep speeding up? Because he had now hit terminal velocity. The air resistance was matching gravity's acceleration. In fact, he started to slow down as the air got thicker and thicker and thicker. So first question. How fast is he traveling in meters per second? What's this question asking us to find?
Meters per second.
That's the units. What's this question asking us to find? VF?
How long was the total, time he was falling?
Patience, let's find out. I have a data sheet, I'll show you. Good question, remember that though. What else do we know?
Do we know acceleration?
Yep. Yep. That would be all the way to the ground. He's not on the ground yet, but we can certainly use time 50 seconds because that's when he hit maximum speed.
And VI and ZI.
Yeah. We watched it. Definitely 0. So again, it's going to be VF equals AT. No square. It's going to be negative 9.8 times 50. Now, we're ignoring air resistance. He's probably going fast enough that air resistance will play a role. I suspect the number that we get is going to be a little bit high, but he was in a near vacuum, so maybe air resistance isn't playing as big a role as I think. Do you all get negative 490 meters per second?
Let's
Speed of sound is 343 meters per second. So Felix Baumgartner became the first human being to go supersonic without a vehicle. Okay? Without a plane or a jet. He was the first person to go supersonic on his own.
What happens when you go supersonic? Like, is there just no noise?
No, there's still sound because the speed of sound, for example, in a jet, the speed of sound through the metal of the jet is faster than the speed of sound through air. So you still hear the noise, and you're in an enclosed bubble of air that's not moving, so you'll still hear sound. Yep, good question.
If you weren't in an enclosed bubble, how fast would you go? Like, literally not hear anything. And there was no plane.
The problem is any air hitting your body would make your skin vibrate, and your eardrums would translate that into sound.
Darn.
Yeah.
Going through that much vibration, wouldn't your eardrums pop?
I'm assuming you're wearing a spacesuit or something.
Yeah.
Okay. Number 2, kilometers per hour. So negative 490. Is it times by 3.6 or divide? Times? Negative 1,764 kilometers per hour. 3. How far has he fallen when he reaches his maximum speed? What's this question asking me to find?
Yeah.
So I know that A is negative 9.8. I know that T equals 50. VI equals 0. I could use the VF if I needed it, but I don't think I need to. In fact, I think I can go D equals VI. Oh, don't waste my time. I don't need VIT. D equals AT squared over 2. Negative 9.8. 50 squared all over 2. That makes more sense because that answer looked way too big to me. You really can't have put in the same numbers if you get a different answer on your calculator. Okay. You folks were asking about the speed of sound. So number 4, it says the speed of sound is 330 meters per second. When does he go supersonic? Okay. What's number 4 asking me to find? More specific. What physics concept is it asking me to find? Which one? I think time. So VI is still 0. A is negative 9.8. But I think that 330 is VF.
Yeah.
I don't know. What's my equation? T equals VF minus VI over A, I think.
Yeah.
Yeah, yeah?
Yeah.
330 minus 0 all over negative 9.8. Uh-oh. Did you type it in? You get something weird. Why can't, what happened?
Negative.
Okay, so that means we've made a subtle sign error. Can you see it?
In the negative 0.
No.
No.
What? Which way is he traveling when he breaks this?
We even wrote that for VF. Why didn't we write on the equation?
I didn't put a negative on VF.
Oh, I did.
Did you? I'm impressed. I left it off on purpose to let you know, hey, if you make a mistake, often the universe will tap you on the shoulder and say, go check your work, please.
Everything's okay. Wow, what would you look at that?
Do you get 33.7 seconds?
Yeah.
So I have a data sheet let's see how accurate we are with some of this. Mission accomplished.
And I'm assuming
Fact sheet.
somewhat inaccurate because of like air resistance.
No, they had sensors on there. So let's find out. Says maximum overland speed was 135.7 miles per hour. That's the wind blowing him in the upper atmosphere. Altitude at which he was dropped. Fastest speed, 1,357.6 kilometers per hour. What did we say the maximum speed was? I think that was our answer to number 2. So a bit of a discrepancy there, and I think that's where the air resistance is playing a bigger role than we realize. When did we say he goes supersonic? How many seconds?
33.7.
They said 34. That's not bad, and I think that's because air resistance, he's still high enough in the atmosphere. Air resistance hasn't played a big role yet because that was earlier on. It's in that final 14 seconds up to that 50. That's when air resistance is starting to slow him down. Maximum vertical speed was at 50 seconds, so we calculated 1,700 kilometers per hour, 1,350. There's air resistance. And then he starts to slow down. At 64 seconds, he goes beneath the sound barrier again because air resistance is slowing him down. And that's what we have a difficulty calculating with our current math, because this is a changing acceleration once air resistance kicks in. Yeah.
What happens if you travel faster than the speed of light? What would it look like?
Can you hold that question? We're going to do a whole unit on Einstein, and we'll ask that question.
Oh.
Okay? It's a good question, but I'll say let's turn that into a teaser of coming attractions.
Okay. Just like when we saw you skydive.
Sure.
How can I know that?
And you can start to hear the wind sound picking up because he's hitting thicker and thicker atmosphere. There's the spin that he went into, and he was spinning pretty fast.
What is he doing? He's spinning, isn't he?
Felix has just gone supersonic, but he's lost control.
Seconds, and stable as a rock. Felix, you calling me? Keep talking, Felix, keep talking. 3 minutes free fall. 3 minutes free fall.
What do you think? I have been following speed for a long time. Sounds like I have to half hour. The laser's smoking up. I repeat, the laser smoking up. If you're at the coldest altitude, the further you fall, the warmer it's going to get. Keep out. Putting my glasses. Really tough. Felix, we're so proud of you. You did absolutely fabulous. Absolutely fabulous. I couldn't have done any better myself.
It's not British, bro. It's like.